Hello everyone. Today we are going to talk about acid-base titrations. So what are the skills we will learn in today's experiment? Well, we are going to acquire expertise in the use of a buret, which is a type of glassware that allows you to slowly and accurately dispense a solution. We will get expertise in weighing by difference. You have watched us do that on the video, but I don't think you've done it yourself. So you'll get expertise in weighing by difference, and you'll get expertise in the accurate and precise measurement of initial standard solutions. And then we'll use this information to figure out the concentration of an unknown solution. So what knowledge will we gain in today's experiment? Well, we will acquire familiarity with pH indicators to determine an endpoint. We will have some understanding of error propagation, and you will gain expertise in analytical report preparation. So the goals for today's experiment, there are two parts. First, we're going to standardize a solution of sodium hydroxide. And then once the sodium hydroxide solution is standardized, and we know its concentration very accurately and precisely, we will use that standardized solution to determine the concentration of a monoprotic acid. We'll be using hydrochloric acid using the technique of titration. So what is a titration? Well, a titration is a method of analysis that allows the determination of the precise endpoint of a reaction. What that means is that we have the exact amounts of the reactants that have reacted with each other with nothing left over. So no limiting reagent here. And what that means is that we know exactly what we have in our Erlenmeyer flask. So the buret is used to deliver one of the reactants. So we have one of the reactants is in the Erlenmeyer flask, and then the second reactant is delivered using the buret. So the standardized solution will go in the buret, and the unknown solution goes in the flask. So we can't see when a reaction is completed. So we use an indicator. In this case, we'll use phenolphthalein. And what happens here is that when we add acid and base together, they will react to form a salt and water. And when the phenolphthalein is in an acidic solution, it has no color. But when it is a basic solution, it will turn pink. So that means that when we're running a reaction, when we go just over the part where we're just going over the part of the reaction where the acid and the base are exactly equal, just a tiny drop will change that color of that indicator from colorless to pink. So in actuality, we go a little tiny bit over the exact point when the reactants and the products, both reactants are in equal concentration, but not too much. And this will allow us to determine the concentration of an unknown. So why do we have to standardize the sodium hydroxide solution? Why can't we just take some solid NaOH and then weigh it on the balance very carefully and determine its mass, and then dissolve it in a very precisely measured amount of water? Well, the reason we can't do that is because we can't weigh out sodium hydroxide accurately. And the reason that we can't do that is because it is deliquescent. And what that means is that it absorbs water from the atmosphere. So when you're weighing out the sodium hydroxide, it's actually in the process of absorbing water from the atmosphere, even in the small amount of time that you take to weigh it out. So what that means is that we don't exactly know what its mass is accurately, because the mass that we determine on the balance will show the mass of NaOH plus a small amount of water. So I found a video that shows how dramatic this can be. So if we look at this video, so what somebody did is put some pellets of sodium hydroxide, and this is time-lapse photography. So the pellets are taking up water from the atmosphere, and that property is called hygroscopic. So sodium hydroxide is taking up water from the atmosphere because it's hygroscopic. But it's a little farther than that. The person who did this video didn't take it. This was time lapse for a day. But if you left it even longer than that, the sodium hydroxide would absorb so much water that it would actually dissolve in the water that it absorbed. So so anyway, the bottom line is that we can't weigh out sodium hydroxide and know that we have all sodium hydroxide and nothing else. We would be weighing out some water at the same time. So what that means then is, since we're going to standardize it anyway, we don't really need to prepare it all that precisely. So we're going to prepare 250 milliliters of an approximately 0.1 molar sodium hydroxide solution. So this is a David Williams observation, is that he noticed that the sodium hydroxide pellets, they're about 100 milligrams each. So his suggestion is to calculate how much sodium hydroxide that you need, and then just count the number of pellets that you need and place them in a beaker. And then we're going to fill the beaker to the 250 milliliter mark. Remember, in the first experiment, we learned that beakers are not all that precise, but again, we don't need to be all that precise. We just need to make a solution that's about 0.1 molar, because we're going to determine exactly what its concentration is in our titration. So if you decide to use this method, please use a spatula or a scoopula and don't pick up the pellets with your hands. Even if you're wearing gloves, you shouldn't be doing that. So add the appropriate amount of sodium hydroxide, solid pellets, into your solution, and stir the solution until the sodium hydroxide is completely dissolved. So you want to make sure it's completely dissolved and that it's homogeneous. So what we're going to do is we're going to standardize the sodium hydroxide with something called KHP. So KHP is just an abbreviation for potassium hydrogen phthalate. So the KHP abbreviation could be confusing because the P doesn't stand for phosphorus. It stands for phthalate, and phthalate is C8H4O4. So the molar mass of this compound is 204.2 grams per mole. So this hydrogen that I underlined right here is an acidic hydrogen. So it's this hydrogen that I'm circling right over here. So that hydrogen is an acidic hydrogen, and in an acid-base reaction, that hydrogen is readily donated. So unlike sodium hydroxide, KHP is very stable in air. If it picked up a little bit of water, we can actually get rid of that really easily by placing the KHP in an oven overnight to make sure it's absolutely dry. So KHP is not hygroscopic. It doesn't pick up water from the air. It's not deliquescent, in which it picks up so much water from the air that it dissolves itself. It's just a nice dry, reasonably cheap compound that we can obtain from a chemical company in a very highly purified form. So what that means is that if we can obtain KHP in a very highly purified form, very dry, and we know it's not going to take up water from the atmosphere, we can weigh this on the balance, and we can be confident that we have the correct mass. So we're going to start by weighing out 4 samples of about 0.4 grams of KHP, and we'll weigh by difference. We've demonstrated to you how to do that before. And we'll place each of those samples into 4 125 milliliter Erlenmeyer flasks. So the samples don't have to be exactly 0.400 grams, but you do need to know what the mass is to the nearest 0.001 grams. So we'll add about 50 milliliters of water. Again, there's no need to measure the water because we've measured the KHP precisely. From the mass of the KHP, we can figure out the moles of KHP using the mass and its molar mass. And the amount of water we add doesn't affect the moles of the KHP, so it doesn't matter if that's been measured precisely or not. And then we'll add 3 drops of the phenolphthalein indicator. So your buret needs to be clean, but it doesn't need to be dry. So it should be clean. You can rinse it with water. But because your buret probably won't be dry, then it will have drops of water clinging to it. So you'll need to take 4 5 milliliter portions of the NaOH solution that you made, and then just rinse the buret a few times, and then discard the rinses. Then what you'll do is you'll fill the buret with the solution, and you want to make sure you remove the bubbles, especially from the tip, before you proceed. So you might want to get some help from either your lab professor or the teaching assistant. We're pretty good at spotting bubbles in the burets, especially in the tips. We have a lot of experience with this. If a tip is completely full of air, it might look like it's full of solution, so we can help you with that. So then you want to take your initial reading on the buret to the nearest 0.02 milliliters. So it doesn't have to be 0. In fact, you shouldn't try to get it on 0 because we're just going to subtract the final buret reading from the initial buret reading to find out the amount of solution that we've added to the flask. So there's no need to take the time that it would take to get it at exactly 0. And we can read the buret to the nearest 0.02 milliliters. That was demonstrated in the video. So when you record your data, you need to design a table in your laboratory notebook, and you want to record the data. So you'll want to have this, the mass of the KHP will need to be in your table, and you'll need to have the initial and the final buret readings of NaOH. So you're going to have 4 samples, so maybe 4 columns would be a good way to design your table. You're going to do a rough titration first, and then you're going to do 3 precise titrations. So in your lab manual, you should distinguish between these types of titrations. So again, the goal is for today's experiment, the first goal is to standardize a solution of sodium hydroxide. So how are we going to do that? Well, we're going to do a rough titration first, or one of my students said he called it quick and dirty. So that means it's a quick titration. We're not going to use that data because we will almost surely go way over the endpoint, but it's a way for us to have an idea of how much sodium hydroxide we need to add. So in the rough titration, what we do is we use the buret and we just deliver a steady stream of our sodium hydroxide titrant to the KHP that's dissolved in the Erlenmeyer flask. So when the NaOH hits the solution, you'll see a pink drop, which will then disappear as the solution is stirring, and it will disappear upon stirring. So what that means is that when the pink takes longer and longer and longer to go away, you know you're close to the end point. So you'll probably end up with a flask that looks like this. It's bright, bright pink. So that's not really considered to be a good endpoint. What this means is if you've added more base than you have acid. And remember, the goal is to be as precise as possible and to add just enough base to react with the acid that's in the flask. So, but that's okay because that's the quick and dirty titration. So it just gives us an idea of what volume of sodium hydroxide to add to the next titrations, and this we want to be very careful. But anyway, in any case, you should record the final volume on the buret. So in the table that you designed, you should record both the initial and your final buret readings, and you can subtract the initial volume from the final volume, and then that will represent the volume of NaOH that was added from the buret to the flask. Okay, so now we're going to do the precise titrations. So what you can do is, if you know how much volume it took and you know that that volume was too much, you can quickly add the sodium hydroxide until you're within a couple of milliliters of where you expect the endpoint to be. So again, and at that point you need to slow down. So when the indicator change, it will change color when the titrant hits the solution, but it will disappear. But when the color takes longer and longer and longer to disappear, you should slow down because that means you're close to the endpoint. So I want you to notice that I did take some photos from the internet to illustrate this pre-lab lecture, but the person in this video is not handling the buret properly. You should handle it the way Dr. Baer does with one hand instead of using 2 hands like is shown here. So ending the precise titration, you want to approach the endpoint more slowly, watch the color of your flask carefully. The other thing is you want to use your wash bottle. So here you can see that there's a drop that is sort of clinging to the end of the tip of the buret. Now, essentially you've already accounted for that in the volume, so you don't want to have a drop hanging. You want to make sure that it gets into the flask. So you can get that drop to fall into the flask by using the wash bottle. And you'll also want to make sure to wash down the sides of the flask with the wash bottle just to make sure that all of the base you added is in fact reacting with the KHP. So when you get really good at this, you can actually add a fraction of a drop. So either you partially open the stopcock and then do a rinse, or you can rapidly spin the stopcock and just do it that way. So whichever way seems more comfortable to you. But again, when you get to be really good at this, you can add partial drops, and that means you can have a really precise determination of your endpoint. So this is what it should look like. It shouldn't be a bright pink. You should have a pale pink. So, and the pale pink will fade in about 10 to 20 minutes. So if you save this flask and then go on to your next titration, you'll find that in 10 or 20 minutes that it will fade, but that's okay. Now, if you're not sure if you're at your endpoint, you think, well, I think I'm at the endpoint, but I'm not sure. You can record the volume reading and then add another drop. And if that other drop makes you go past the endpoint, well, then that's okay. That means that you were right, that you were at the endpoint. And since you have recorded that volume, then you'll be able to use that volume as the volume at which you reached your endpoint. Okay, so today's experiment, what are our goals? The second goal is now we have our standardized solution and we want to determine the concentration of a monoprotic acid. Again, we're going to use titration. So first, before we do this, we have to calculate the concentration of our sodium hydroxide solution. So what we did is we took this is our KHP, and there's that acidic hydrogen, and the KHP was in the flask. The sodium hydroxide was in the buret, and when the sodium hydroxide was added to the KHP, the hydrogen on the KHP was donated, and the hydroxide ion here, the proton and the hydroxide ion combine to form water. And then there's your water, and this is your salt. So it's a sodium potassium phthalate salt. So you notice that there's a 1-to-1 mole ratio here. So we know the mass of the KHP, we know the molar mass of the KHP, so we should be able to figure out how many moles of KHP we had in our flask, and then that will be equal to the number of moles of NaOH because of this 1-to-1 stoichiometry, which you should account for and show in your sample calculations. And once we know the moles of the NaOH and we know the volume of the NaOH, then we have the concentration of the sodium hydroxide in moles per liter. So using the data, the mass of the KHP and the volume of the NaOH added, we can use the data to calculate the precise concentration of the sodium hydroxide solution we made in units of moles per liter, or molarity. And it should be reasonably close to the 0.1 molar estimated solution that you try to make. Okay, so now you're going to get a solution of hydrochloric acid, and those will be prepared by Dr. Williams. So please don't forget to record the unknown number in your notebook, because we will need to check that to see if you got it right. So now you're going to use a volumetric pipette. You did this in the first experiment, so use your very best pipetting technique that you learned in the first experiment, and you're going to measure out 4 10 milliliter samples of the unknown solution into 4 125 milliliter Erlenmeyer flasks. And then you want to add between 20 and 30 milliliters of water, and that's because 10 milliliters is not a very large volume to use in a titration. And again, it doesn't matter how much water that you add, because that doesn't affect how many moles of the hydrochloric acid that you add. So add some water, add some phenolphthalein, and now you want to design a second table. It should look pretty much like the first one, and again, you're going to record the data that you collected to determine the concentration of your unknown hydrochloric acid solution. So you're going to have 4 samples of HCl. You'll need a minimum of 3 good titrations. So that's why there's a possibility of doing a fourth. If there's one of your titrations in which maybe you went over the endpoint, maybe you do another titration so that you have 3 good data points. So you'll need to record the initial and the final volumes on the buret, again, so that you know how much NaOH you added in milliliters. So once you've done that, so you'll do the titrations the same way you did before to a nice pale pink endpoint. So once you've done that, you're in the position of being able to calculate the concentration of the unknown acid. So first you need to write the balanced equation for the reaction of NaOH with HCl. So it'll be similar to the one that I wrote for NaOH with KHP. And then now we know exactly the concentration in moles per liter of the sodium hydroxide solution. So from that volume from that concentration and the volume that we added, we can figure out how many moles of NaOH we added. Then we should look at our equation and look at the stoichiometry to figure out the mole relationship between NaOH and HCl. And then once we know the moles of HCl, we know that we added 10 milliliters of the HCl, so we should be able to figure out the concentration of the HCl in moles per liter. So you want to have 3 good titrations, so we can calculate the average and the standard deviation. So if you're happy with your precision, you can stop right there. But if your standard deviation is a little high, maybe you want to perform an additional trial, because now you have a lot of practice and you're very good at this. So an additional trial will probably be a high quality one. Okay, safety notes for today. So when you're working with NaOH pellets, again, don't use your hands, use a spatula or scoopula, but you should still be wearing gloves. Once you've made the sodium hydroxide solution, it's fairly dilute. As long as you're careful, it probably will be easier to do the titration without gloves. So just decide how you are comfortable with that. The hydrochloric acid solutions that we're giving you are also not very concentrated. Still though, if you decide to do the titration without gloves, if you spill any NaOH or HCl solution on your skin, you should rinse your skin with copious amounts of water. Both of these reagents are corrosive. They cause minimal damage if they're in the dilute solutions that we're giving you, but still, if you spill them on your skin, you should wash your skin very, very thoroughly. So today, an analytical report is required, so you'll have your results and the calculations and interpretations in well-organized tables. You need to show your sample calculations. So sample means just one of each type. So you're doing trial 1, trial 2, trial 3. We don't need to see all 3 trials. You can just show us trial 1. You should use the Microsoft equation editor. Some students did this last time, but not everybody did. This is a skill that we want you to have. I made a video for you so that you can see how to do that. So if you don't know how to use the equation editor, please look at the posted video. You need to carry out an error analysis, so you should, after your sample calculations, you should have a nice little paragraph where you carry out the error analysis that we ask for in the laboratory manual. And also, because this is an analytical lab report, you should, we know that part of the grade will be based on the quality of your work. So before you submit your report, you should look at the sample report in Appendix B in the lab manual. There is a rubric posted, and your own lab report from Experiment 3, the barium sulfate lab report that you wrote for us. That was your first analytical lab report. So what you should do is go back to that lab report and look at the comments that your instructor made. So if there are any mistakes that you made, you don't want to repeat them on this lab report. So I thought what we could do is we could end this video by, I wanted to show you that this turn in lab reports tab on Sakai that we've been asking you to use to turn in your lab reports, that there are a lot of really good resources here, and I wanted to point them out just to make sure that you knew about them. We don't have a link now, but we'll make sure that we have a link to the assignment for Experiment 5. So I'm going to skip over the full reports, because we're doing an analytical report. So here we have the Analytical Lab rubric that we're using to grade your report, and we have the appendix, which shows the sample analytical report. So if you look at this sample, there's an example lab report, and there are some boxes with some blue text that explain the kinds of things that you need to pay attention to when you're preparing your report. There's a video that I prepared earlier, and down here is a video that shows how to use the equation editor. So, and as I said before, consult your own Experiment 3, the determination of a sulfate by gravimetric analysis, because that report was an analytical report. And again, you want to make sure that you don't make the same mistakes. So that's it for now. We will see you in lab, and we will look forward to that. And I hope this is helpful, and see you on Tuesday.